we were doing radioactive decay. This was our topic. This was our topic in our class, radioactive decay, and we had a concept that what happened during radioactive decay, that some nuclei are unstable. Some nuclei are unstable. They emits alpha or beta particle. This changes their atomic number, the element changes, and the radioactive decay occurs. This is a concept here, and it is necessary to remember. This is necessary to remember that decay occurs for an unstable nucleus. Decay occurs for an unstable nucleus. The nucleus is unstable. It emits alpha, beta rays. The parent element converts into daughter element. There are two types of decay, alpha decay and beta decay. And gamma rays do not cause any decay, even though they are emitted. They are emitted, but they do not cause any decay. Alpha decay, when alpha particle is released, it is a packet of 2 proton and 2 neutron. Alpha particle is a packet of 2 proton and 2 neutron. So the atomic number decreases by 2. Atomic number decreases by 2 and the mass number decreases by 4. Then we had written these examples also. Now, remember that when you say nitrogen 15(7), they are actually isotopes. I think you had written these examples, if I'm right.
Yeah.
So write under it that commonly the products are isotopes commonly the products are isotopes which may be stable or so the output of these reactions, may be stable isotopes, or they may be unstable also. Unstable means they would also be radioactive. This is called alpha decay. Nitrogen 15(7) is an isotope. Actual nitrogen is 14(7). Now, uranium-238 converts into uranium-234. This is also an example of alpha decay. So now copy this example.
Done.
Now, examiner can ask you if you remember this master equation, okay? And examiner can ask you to fill in the space, the missing particles. Look at this equation and guess which particle is missing.
Alpha.
you had a list of particles. Remember, if you look at your notes, you will find a list of particles. Look at, this is the list of particles. Look at the list of particles and look at the list of particles and let me know what element is missing. What element is missing here? This is the list. See the difference, 39 becomes 38. Just like you balance chemistry equations, 39 and 38, difference is 1. 19 and 8, difference is 1.
Proton.
So look at the list of particles. Look at the
Proton.
which from the list. So
Proton.
just a minute. I show you 39 minus 38, 1. And the atomic number is 19 minus 18 is equal to 1. So which number is now among the list? Select which is 1, 1.
A proton.
The proton. Good. This is how you solve these equations. These are commonly in your MCQs also. Now we are putting our idea of energy transfer. We have already written this equation, and in these processes, alpha decay, beta decay, some mass converts into energy. In alpha decay, beta decay, some mass converts into energy. This is Einstein equation, and due to this equation, some mass converts into energy. So right under it, that during right under it, that during alpha decay, during alpha decay, some mass, so just make a correction, during alpha or beta decay, some mass converts into energy. This is equal according to Einstein equation. This is according to Einstein equation. You have to copy now this is screen. During alpha or beta decay, some mass converts into. This is the Einstein equation, and E is equal to mc square. It's only symbolic. in the new course, no calculation needed on this formula. No calculation in syllabus now. So this formula is only symbolic. This formula is only symbolic. Examiners do not give calculation on this. Energy, what happens to the energy release? Some energy converts into X-ray photons. Some energy becomes kinetic energy of daughter nuclei. Some energy converts into heat. Some energy converts into other particles like alpha. So our next concept, the energy released converts into these things. So let's make our next concept for today. These reactions release a large amount of energy. What happened to that energy? It converts into gamma ray photons. It converts into kinetic energy of daughter nuclei. It converts into heat. It converts into kinetic energy of other particles. You have to copy this list.
What does EK mean?
EK means kinetic energy.
No.
Now give a heading, beta decay. Beta decay, beta particles are high-speed electrons. So when beta particles emit, they are like electrons. You have to now copy this screen.
Done.
Now, alpha particles are helium nuclei. Beta particles are electrons. Particles are emitted, mass number does not change. Mass number does not change, but atomic number increases by 1. So you take chemistry also. So it is easy to understand that atomic number is everything. Everything is atomic number for an element.
Because if the atomic number changes, the element changes.
Yes, atomic number changes. If atomic number changes, everything changes. So the first point, remember, A, which is nucleon number, no change. In beta decay, mass number or nucleon number does not change. Copy this screen. Increases by 1.
And
Now this is the formula. Remember that alpha and beta, there are two types of decay. Okay, now I had shared with you some animated images also, and if you had look at them, alpha decay or beta decay, whatever is decay, it is coming from the nucleus. All types of decay are coming from the nucleus. So decay is a nuclear process. Gamma rays are actually photons energy. Now you have to copy this screen.
then
Now look at these two examples. Fluorine 19,9. Look at the decay. After decay, mass number is still 19, but atomic number increases by 1. Then magnesium 2412, aluminum comes in. The name aluminum is not important, but the numbers 24, 13, 0, -1, you have to balance the numbers. Now you have to copy these two examples. No need to copy the equation again. Just copy what I'm ticking. Now look at this formula again, but this time I'm using beta as a beta symbol directly. Look, 14 is not changing. This is a very big symptom in the paper that this is a beta decay. 6 becomes 7. You have to copy this screen.
Which symbol are we supposed to use? This one or the
The
remaining
symbol
two?
official symbol is E. Official symbol is E.
Done. Done.
Radioactive decay series. It's a formal concept that sometime the decay process continues, and after one decay, the product is also radioactive and it further decays. Remember, when alpha decay occurs, atomic number decreases by 2. When beta decay occurs, atomic number increases by 1. So sometimes it happens, for example, 1 alpha decay is equal to 2 beta decays. So after one decay, what will happen? That maybe after one decay, atomic number is decreased by 2. And after that, if 2 beta decays occur, it will be the element will be back. Look at this example. Sodium 2311 becomes F199 after one alpha decay. Then look at this. Then after that, a beta decay occurs. It becomes 1910. One more beta decay occurs. It's back on sodium. Start was sodium and end is sodium. Sodium is back. This is called radioactive series. This is called radioactive series. Now copy this.
Done.
And after that, copy this screen.
Done.
This is the example. Look, we started with sodium. And after 3 decays, we are back on sodium. You have to copy this.
Done.
Radioactive decay is a random and spontaneous process over space and time. This is our next concept for today, that radioactive decay is a process which is random. Random means something which is not predictable. Random means something which is not predictable, and spontaneous means something which occurs itself. So radioactive decay is a random and spontaneous process. It occurs itself. You can't control it. Random means you can't predict it. Like earthquake is a random process. So it's a random and spontaneous process. You have to copy this.
Done.
Now, what's the meaning of random? Random means there is no way to tell which nucleus will decay and cannot predict when it is going to decay. There is an equal probability of decay. There is an equal probability of decay. So the process is random in terms of direction and time. Which nucleus will decay, and in what direction it will decay is not predictable. Spontaneous means the process is not triggered by any external factor like temperature or pressure. So what is meaning of random? That there is an equal probability, of decay of any nucleus. So now you have to copy this screen.
Done.
So now see the word concept of spontaneous. So spontaneous means that if you change the temperature, you change the pressure, they won't affect anything. Temperature, pressure, they won't affect the process. The process is independent to it. So you have to copy this screen.
Done.
This is a sample. Fluctuations are there. This is a wavy sketch which shows that there are fluctuations. Randomness means this. Random means something which is not ordered. When you say the word random, so the GM tube count rate fluctuate. Look at this screen. The GM tube count rate is fluctuating until it reaches the background count. And radioactive source is there, and you can identify this is a GM tube. So now you have to copy this. When you are practicing at home, that you should try to you should try to focus on current of electricity, because this is where you can work a lot and you will have good amount of time for that, because presently we have nearly finished all the difficult chapters. But electric current is a real trouble when you're doing past papers.
Thank you. Done. Done.
Now, the concept says when you change the temperature or you change the pressure, spontaneous means no change will occur. The graph does not change. It means temperature, pressure, they are not going to make any change. This nuclear reactions are independent to temperature changes, pressure changes. Now, give a new heading, nuclear fission. Give a new heading, nuclear fission. Now, first make the concept that you have a heavy nucleus, a big nucleus.
Is it when the heavy nucleus splits into two smaller?
And you send a neutron, and the nucleus breaks into smaller nuclei along with some neutrons and a lot of energy. This process is called nuclear fission. So what is nuclear fission? When a slow moving neutron strikes a heavy nucleus, the nucleus splits into two lighter nuclei along with some neutrons and a huge amount of energy. This is called nuclear fission. So nuclear fission is a process where a heavy nucleus breaks down into lighter nuclei, but the process releases a huge amount of energy. You have to now copy this.
Done.
This is a heavy nucleus and a neutron is coming towards it. This is a heavy nucleus and we are sending a neutron towards it. Neutron is captured by the nucleus. Neutron is neutral, so no one doubts on neutron, and neutron easily gets inside it. This is what happens when the neutron gets into the nucleus. It breaks the nucleus. It breaks the nucleus and releases a large amount of energy. This is a schematical diagram that how this process occurs. Now you have to copy this screen.
Done.
So this is called radioactive nuclear fission. This is a better visual picture that a heavy nucleus doesn't have a boundary. Nucleus does not have any boundary. So nucleus is just like a collection of nucleons. So proton happily gets inside and breaks the nucleus. Look at this diagram. Nucleus nucleus is capturing the neutron, and it's breaking down into two lighter nuclei. There are different equations which can be written, and again, you're not supposed to remember these names of chemistry, uranium, beryllium. So what you are supposed to remember is the balancing. The numbers in the top line sum up to the same on both sides, and number in the bottom lines should be sum up to the same. This is very important to remember. Now, right under it, different equations can be written for nuclear fission. So this is an example. Copy this equation also. Copy this equation. I'm just coming. Copy this equation. a very large amount of energy is released according to Einstein equation. Again, remember that calculation is not in course now on the basis of this equation. What you have to remember that energy is released according to Einstein equation. So there was these calculations were there. Now, after the syllabus update, they say that these calculations are not required. And I have shared with you the syllabus changes. So when you are doing past paper, you can find it very helpful. Energy converts into gamma rays, converts into heat, converts into kinetic energy. Nuclear fission is a chain process. Look at this concept that this process does not stop. It is just like putting some fuel on fire. So when you put some fuel on fire, it goes on. So what happened here? Look at this screen that you are sending the first neutron. Fission occurs. This is happening fission. Now look at these neutrons which are released. These neutrons will cause fission in nuclei and further neutrons are emitted. So once you start this process goes on. Once you start this process goes on forever. It is like a chain process. And this process releases a huge amount of energy. And why it releases such a huge amount of energy? According to Einstein equation. According to Einstein equation, this process is highly exothermic. Look at this animation. This is called nuclear fission. This is called nuclear fission. It is a chain process. What's the meaning of chain process? That once you start this reaction, it will go itself. It will be automated. It will be automated. Look at this animation. This is called nuclear fission. And look, this process is a chain process. So once you start this process, it goes on itself. This is also a good animation, but its language is different.
La reacción en cadena se produce cuando un átomo emite un neutrón, que a su vez choca con otro átomo y produce la fisión, o sea, la división del átomo, emitiendo más neutrones que impactan con más átomos. Con cada fisión, más cantidad de materia se convierte en energía. Si se concentra el uranio 235 de forma adecuada, en una millonésima de segundo se producen suficientes fisiones para...
So this is a very nice explanation what happened. Applications of, then you have to copy now. You have to copy this screen.
And
Now, there are two applications of nuclear fission. One is a peaceful nuclear power plant. Second is destructive nuclear bomb, nuclear weapon. You have to copy now this thing.
Done.
Now, give a side heading. Give a side heading, nuclear power plant. Nuclear power plant is a peaceful application of nuclear energy. Look at this diagram. This is a nuclear reactor. This is a nuclear reactor, and here, this is a nuclear reactor. It is generating heat. It is generating heat, and then we are pumping the heat to boil water. We are boiling water from it, and we get steam. Steam is used to turn the turbines, and turbine runs to generate electricity. This is the purpose of, this is the working of a nuclear power plant. We have a nuclear reactor, a boiler, turbine, and generator. They convert nuclear energy into electrical energy. You have to copy this screen.
Done.
This is a nuclear reactor. A nuclear reactor works in this way. And I have to show you an animation so you can understand how a nuclear reactor works. Remember, every power plant in the world, every power plant is actually generating electricity. The power plants are designed to generate electricity. It's a very nice animation, but without a sound. So you have to look it very carefully. This famous dome shape is a nuclear reactor, a famous dome shape. Inside it, this is the highly technical nuclear reactor, and these red glowing rods are generating heat. This is nuclear fission going on. This is fission. Then heat energy is produced. The process, the steam goes back. Look what happens to electricity. Then electricity is supplied to the town. So we stop here and we will inshallah continue this in our next class. Can you tell me one thing, that